All right, today is an exciting day because we get to talk about the Pythagorean theorem. And you've probably heard people talk about this before, and you have no idea what they're talking about. So I'm going to talk about what it is and what it means. So the important thing about a Pythagorean theorem is you're going to talk about triangles. So here's a triangle, okay? Specifically a right triangle. That means you have a 90-degree angle. So it only works on a right triangle. So I'm just going to kind of sketch this, guys, so you see it. I know it's a little bigger than it's supposed to be. But we need some definitions. Number one, Pythagorean theorem works with the right triangle. So we use this angle measure right here, that little square, to show that this is exactly 90 degrees, exactly a quarter of a circle going from here to here. Okay? But the length and the sides can be anything else. Like you can have it like this. Any right triangle works, right? So then we have two, what we call our legs. So this is a leg right here, and this is another leg. They're not the same leg. And this, we have a fancy word for it called the hypotenuse. And if you forget the word hypotenuse, just remembered occupied restroom in an airplane. And you'll remember it. Hypotenuse. Okay? So that's the word for that. And there are two legs. The legs are always next to the right angle. The hypotenuse is always across. And you can tell that the one across is always the longest. Hypotenuse is always the longest, and these are always shorter. No matter how I draw my triangle, I can't draw it so that this one is shorter than this, the one across the right angle. And you know this because you cut across lawns and sidewalks, and you say, I have to get from here to here. Well, you're going to go straight here, right? Now, that's longer than either of these legs, but it's actually shorter than both of them added together, right? You're going to take your shortcut. You know, since you were 2 years old, you knew this is the shortcut, but it's still longer than one of the directions. All right, so legs and hypotenuse, or hypotenusi, or whatever. It's like hippopotamus, hypotenusi, whatever. So those are legs and hypotenuse. And what the Pythagorean theorem says is it says if you have the length of one leg and the length of another leg, you can find the length of the hypotenuse without measuring. So what it says is if this length is A, so we don't know what it is yet, and this length is B, and this length is C, still we don't know what it is, we could say, this is cool, A squared plus B squared equals C squared. That's a little bit weird, okay? It's not A plus B equals C. That can't be true because you know this is shorter than both of these. It's A squared plus B squared equals C squared, which is a little bit weird. So we're just gonna measure this triangle and see if it works, okay? So I have this triangle here. I'm gonna actually get a ruler, and you can't just tell me a theorem and just tell me I'm supposed to believe you. Right? So I'm going to say, no, what are you talking about? So I'm going to measure this. My actual measurement here is 7.8 inches. Okay, so you can kind of see that right there, 7.8. And then this one here looks like 4 inches. Okay, I'll put inches sign, okay? And then I'm going to say, let's see, what is this length here? It looks like 8.75 inches. Okay, so that's just approximate. So let's just see if this works. Well, here's one leg. I have 4 squared plus 7.8 squared. Does that equal, I'm going to put a big question mark there. Does it equal 8.75 squared? And so I'm going to get my calculator out. I could do 4 squared in my head, but I can't really do 7.8 squared in my head. So I'm going to say, is this actually true? No, I got a little messy there. 4 squared I know is 16 plus, so I'm just going to do 7.8 squared. I got 60.84. And then I put a question mark over my equal because I don't know yet. I don't believe it. 8.75 squared. I got 75.5625. So now I'm going to just add these. 60.84 plus 16. I got 76.8 76.84 equals 75.56. Now, if you're a stickler, you would say, well, those are not equal. We just disproved the Pythagorean theorem. But if you know that I'm not very neat and organized, I probably measured this a little bit wrong. So I would say these are pretty darn close. And considering that I just did a rough cut, my edges aren't perfect, I would say, you know what, this kind of shows it kind of does work. Okay? So I'm gonna say I think it sounds crazy, but true. 16 and 60 is about 76, you know, just with plus or minus a little bit. Now, the Pythagorean theorem says, in actuality, if I drew a real triangle and measured it accurately, they would be perfectly right. And so now what we're going to do is like kind of a fun proof of the Pythagorean theorem. Now, I know a lot of different proofs for the Pythagorean theorem, and every time I find a new one, it's very exciting because they're so interesting. So this is a geometric proof. Geometric proofs kind of show shapes and area to prove something. I know, you can prove it using trigonometry and ratios and all that, but here's just one thing. So let's leave that guy alone for a second. Let's go back to our same triangle. Remember we said this is a length and this is length. So I'm going to call this length A and this length B and this is C. And if I wanted to know the area of this triangle, you remember area is 1/2 base times height. Remember, because if I had two of them, it would be area is A times B. So one of them, I would say area of one triangle is 1/2 A times B. So if I knew these lengths, I could find the area. All right, so you need to remember that in the back of your head. So now I'm going to do something fun with the triangles. Okay, remember that the short one is A and the long one is B. I'm going to just arrange 4 triangles. Okay, so 4 triangles here. So I want to say, what is the area of this big square? I can find it. Okay, so this is the same as here. I made this other square so you could see. If I'm looking at the area of this purple square, right, it's going to be the same as the area of this whole thing. Now that's the green, including the white. So the area is the length times the width. And I say, well, I don't know the length and the width, but I know this is A, and I know this is B. So this whole length is A plus B. And this length right here is A plus B. So the area of the purple square, right, is, we'll write it up here, area of the square equals A plus B times A plus B. Okay? So let's just make sure you get that in there. Okay? Now I'm going to rearrange. Okay? So this is the fun part. So I'm going to just pull this guy up here, and I'm going to pull this guy up here, and I'm going to pull this guy right here. Okay? And I'm going to talk about this. Now, if I drew in this, okay, well, we know that's A plus B, but we're gonna use some different information now. Where's my eraser? Now we know it's A plus B and A plus B. Fine, we already got that part. Now I'm looking at this right here. What is this? I can find the area of each rectangle and square separately. Now this right here, this square is this long leg length, which is B. So this is B squared. That's the area of this square. Now this is A, so this little area is A squared. Now what is the area of these 4 green triangles? Oh, well, I already know the area of one green triangle, right? So I have A times B, so I have 1/2 A times B. I have 4 green triangles, so 4 times the green triangles is 2AB. That's the area of the 4 triangles. Area. Okay, so I could say the area of this shape is all 4 of these added together. So I get A squared plus B squared plus 2AB. Okay. All right, so we got that. Now I'm just going to have to mess around because what I really want to do is find the area in terms of c squared. You remember that. So let's go back to here. Here we go. Let's go back to our other thing. I'm going to cover this guy up. So you guys know that the area equals this because we added up the rectangles. And we also have the area is this. Now let's do this again. This length right here, there we go. Let's look at this rectangle. This rectangle has a side length of the diagonal, which is C. So this area of, sorry, did I say rectangle? Special rectangle is C times C, which is C squared. So that's this, okay? So plus the four triangles, which we already know is 2AB. So we could say this whole purple square, purple, is the same as the middle big square, C squared, plus again, 2AB, because that is all four of these. There we go. Look at that. So I have the area equals this, and I have the area equals this. Well, if you have two areas that are the same, you can say they're equal, okay? They are equal because they're the same thing, right? Then look at here. We have c squared plus 2ab equals a squared plus b squared plus 2ab. But I'm like, oh yeah, we have our, what is it called? Subtraction property of equality. So I could just subtract 2ab from both sides, and it should be equal. So if I subtract this, it goes away, and then I get a squared plus b squared. What? That's so weird. That's the Pythagorean theorem. So we actually kind of just proved geometrically the Pythagorean theorem, which is kind of weird. But oh well, we did it. It's one of those theorems that like I'm using for 20 years, and I still feel like it has this miraculous properties to it. It's really fascinating. There are people who studied this for hundreds and hundreds of years, like people like Pythagoras and all of his students. So here's an example of how you would use this in your math book. You'd say, here is a triangle, and it's a right triangle, and I would need you to find the missing side. So you would say, well, I know that a squared plus b squared, these are always the legs, equals c squared. The hypotenuse is always by itself. And so I would say, well, 64 plus 15, I don't know what 15 squared is. I think it's 225, actually. 225 equals c squared. And now you're just back down to algebra. Let's see, 25 plus 64, 6, 7, 8, 289 equals c squared. Now, if you know your squares, that's great. If you don't, you go 289 square root of, and you get 17. So you get c equals 17. Now, that's a very pretty number. It's a whole number, you know. That's nice and convenient. Does that always happen? Let's try one more and see what happens here. 20 something and 29. Now here you got to be a little careful because one of the legs you don't know, right? You know the hypotenuse. So make sure when you do your a squared plus b squared, I'd always write this out. A, you could say is 20 squared plus, now you need to say this. This is your question mark. Leave b squared as a b because you don't know what it is. C squared is the hypotenuse, 29 squared. Okay, now we do this again. 400 plus b squared equals, I have no idea what 29 squared is. 29 squared, 841. Solve for b squared, 441. So I need 441, the square root of that. Oh, look at that, b equals 21. Again, another whole number. Now, just a word to the wise, it's usually not whole numbers. If you're taking a real measurement, of something and really trying to find the diagonal, you're not going to get these beautiful triply numbers, 8, 15, 17, 20, 21, 29. These are actually called special numbers. They're called Pythagorean triples. And there are tons of them where they actually work out to whole numbers. But in reality, in your real life, you're not going to get those. So I'm going to give you an example. I'm just going to draw a random triangle and see what happens, okay? So here's a ruler, and we're gonna measure it. So I'm just gonna draw maybe here. Definitely need a right angle or it won't work. And I'm just going to draw, like, let's say, how about this? Okay. So what happens is usually, like, maybe you're trying to see how long it is to walk across your room, right? Here's your bedroom. And it's really easy to measure this side and this side, but it's kind of hard to measure this side, right? Because it's not lined up against a right angle. So you would go and you'd go to your room and you'd say, well, this looks like 28. And this is probably centimeters, but your room is probably feet. And this looks like 24. And so you'd say, well, how do I find the diagonal across? All right, so let's find it using the Pythagorean theorem first, and then we'll check it by measuring. So 24 squared plus 28 squared equals c squared. Calculator time, 24 squared, 576, 28 squared plus 784. And then I add them together. 1360. And then I take the square root. Ooh, I get a yucky number. C equals 36, I'll just say 0.87. So probably I'm going to say round it to the nearest 10th, 36.9. That's what I got for the hypotenuse. So let's just check. So here I got 35, 36. Actually, yeah, that's pretty close. Looks to me like 36 and a half. But it could be 36.9. It kind of depends on where I measured on my marker, because my marker has a thickness. So yeah, I would say verify the Pythagorean theorem works for this. Now, usually you get numbers that are not whole numbers. That's okay. You just have to use your square root button. But there are a lot of fun Pythagorean triples, like, 3 squared plus 4 squared equals 5 squared. 5 squared plus 12 squared equals 13 squared. And we just did a couple more examples there. So that's it. Enjoy solving for legs and the hypotenuse of your triangle. Goodbye.